Guys, Mrs. Traver here. Today we're going to talk about special right triangles. As my students in class like to call it, these are the cheat codes to right triangles. In this case, we're going to have our learning target of being able to recognize the similarity in all 30, 60, 90 triangles and notice the ratio between these side lengths. You know you'll be successful when you can notice the special right triangle and that it has a scale factor to help you solve for sides. Let's first, though, review some radicals. This is a skill from last year, probably for most of you, and I think we need to review it for a moment. So let's simplify each of these. And when I say simplify, by the way, the smallest number possible has to be inside the radical, and also there can be no radicals in the denominator. Those are rules of simplifying radicals. So let's start off, and let's notice that there's a property with radicals that if you have the same base, meaning this is both a 2 in here, it's kind of hiding, but these are both square roots. We can combine underneath the radical to be 5 times 10 inside there, which we know is 50. And then the way to simplify this is to look for the largest perfect square that is divisible into this number. So if I think about perfect squares, let's make a list. By perfect squares, I mean the number that was squared is it. So 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared, and so on. So if we look at this list of numbers, I want to find the biggest number possible that goes into mine, 50, which I can see is 25. So I'm going to rewrite this as 25 times 2. And I know the square root of 25 is 5, and the square root of 2 is going to stay on the inside. So I've rewritten root 5 root 10 as 5 root 2. Let's do the next one. We know with simplifying we can't have a radical on the bottom, so we're going to do something fancy here. We're multiplying by 1, which seems weird, but not just regular 1. I'm going to multiply by a fraction, which is a number over itself. So the number that I pick is actually very intentional. I want to undo the radical on the bottom, and to do that, I'd have to multiply it by root 3. But I can't just multiply the denominator by root 3, so let's multiply the numerator by it as well. Therefore, multiplying by 1, which isn't going to change the number, but will change how it's written. My top now is 5 times root 3, or 5 root 3. And my bottom is root 3 times root 3, or root 9. We know the square root of 9 is 3, so let's replace that. We've got 5 root 3 over 3. This is our simplified radical. We'll see these within the problems on special right triangles. To get us started, I want to show you where in the world this came from. So let's start with the triangle we know stuff about. It's an equilateral triangle, which means it has equal sides and equal angles. And they told me that it's a side length 2. So I'm going to fill in all the information I know, which is that all of these sides are 2. And I also know since it's equal angular and all the angles inside of a triangle sum to 180, that these each must be 60 degrees. What we're being asked to do here is solve for the height. So let me draw a height in. I'm going to kind of dash a line in. And I see I've got a right triangle. I'm going to actually kind of peel that right triangle off and put it to the side. And let's look at it specifically. So here is that right triangle. I don't know the height, so I'm going to put an H there. I do know this angle was 60, and I do know this side was 2. I also know that since I cut this angle in half, this angle must be 30. And since I cut this bottom side in half, this side must be 1. Let's solve for h, but instead of using sine, cosine, or tangent, let's just use Pythagorean theorem. I have 1 squared plus h squared equals 2 squared. To solve, I'm going to get rid of the squareds by squaring them, and then I'll subtract the 1 from both sides and square root. So I now have the height of this equilateral triangle is root 3. This relationship that you see here with the triangle that has angles 30, 60, and 90, and side lengths 1, root 3, and 2 is special because as we know with similar triangles, you can scale any triangle up or down by just stretching it bigger or smaller. All the angles will stay the same and all the sides will be proportionate. That's the crux of today's lesson. If you'd like to, this is a great slide to pause and write down as a reference for all 30, 60, 90s. Let's jump into our first problem. I've got that picture that you had on the last slide down for us again on the left. And then there's a new triangle that's been rotated and dilated. This is not to scale, by the way. Let's see if we can match sides up. Since I know that I've got a 30 and a 90, this must be 60. So since these are similar by angle, all their sides are proportionate. The side across from the 30-degree angle is 15 on our triangle, and the side across from the 30 on the original triangle is 1. I can tell it went from 1 to 15, so my scale factor is times 15. If I know that, I can find sides N and M pretty quickly. Usually across from the 90-degree angle is 2, but now I have to multiply, so it is 2 times 15, or 30. Usually across from the 60-degree angle is root 3, but now I have to multiply and it's 15 root 3. That's it for these kind of problems, guys. Let's move on to another one. Here it is, and let's see what we were given. We were given what's across from the 90. What's normally across from the 90 is a 2. So I can tell my scale factor. I like to write that down to the side. My scale factor here, 2 times 3 is 6. So my scale factor was 3. I can fill in the rest of the sides now. This is a 30-degree angle, I know. So across from it is normally 1, but now it's 1 times 3, or 3. And lastly, across from the 60 is normally root 3, but now it's 3 times root 3. Let's try another. Number 2. On this one, we were given what's across from the 30. Normally across the 30 is 1, but now it's a 10. So my scale factor is times 10. So now across from the 90, instead of being a 2, it's 2 times 10, or 20. And across from the 60 is normally root 3, but now it's 10 times root 3. Let's see what happens here. We were given what's across from the 60 is 9. Normally across from the 60 is root 3. This one's got a little bit more going on here, because finding a scale factor isn't as simple as the last ones. Normally I was able to quickly realize with multiplication facts what my scale factor was, but this time it's harder to find. I know that my scale factor was root 3 times something to get 9. It got bigger by something. We just don't know what that something is. So let's solve for x being our scale factor with normal algebra. I'll divide both sides by root 3. And I've essentially got x already now, but I can't have it written like this because I can't have a radical on the bottom. So let's multiply top and bottom by our root 3, where on the top we have 9 root 3. On the bottom, root 3 times root 3 is root 9. Root 9 is 3. So if I trade that out, we're looking better. There's no radical on the bottom. I can do one more thing to simplify though. 9 over 3 is 3. So my scale factor is 3 root 3. That's my scale factor. So that part was a little harder to come by on this problem. That's why we reviewed radicals first. Let's see what we can do with this problem now that we know our scale factor. What's across from the 30 is normally 1. Now it's 1 times 3 root 3. So 3 root 3. And normally across from the 90 is 2. Now it's 2 times 3 root 3, or 6 root 3. This is as tricky as they come, guys. I hope this has been a good review of 30, 60, 90 triangles. In the next video, we'll do 45, 45, 90s. See you then.